For 170 years, one unsolved question has sat at the very center of mathematics, untouched by every genius who ever tried to break it. Then, in 2026, a research system built by an AI lab did something no human mathematician had managed in over a century and a half. It moved the needle. Not by guessing, not by luck, by grinding through millions of tokens of reasoning, chasing dead ends, discarding failed approaches, and slowly, carefully, finding a crack in a wall that had not moved since 1859. This is the story of what actually happened, why it matters, and why the honest version of the story is far more interesting than the exaggerated one flooding your feed. To understand why this is such a big deal, you first need to understand what a prime number actually is. A prime is any whole number greater than 1 that can only be divided evenly by itself and by 1. 7 is prime. 9 is not because 3 goes into it evenly. These numbers are the atoms of arithmetic. Every other whole number is built by multiplying primes together, and nothing else can be broken down any further. Simple to define. A child can list them. And yet these small, ordinary-looking numbers have humiliated the greatest mathematical minds in history for over 2,000 years. Here is the strange part. Primes never run out. No matter how far you count, there is always another one waiting further up the number line, and this was proven more than 2,000 years ago with a short, elegant argument that is still taught to students today. That much mathematicians are completely certain of. But knowing that primes are infinite tells you nothing about where they actually show up. Some primes sit right next to each other, separated by just 2. Then there are long stretches with none at all. There is no formula you can plug a number into and get the next prime out. You can only search one number at a time and see what you find. It looks like static. It looks like noise. And that has always deeply bothered mathematicians, because mathematics is supposed to be the one place in the universe where nothing happens by accident. The first real progress came from Carl Friedrich Gauss, working around the year 1800. Gauss spent countless hours counting primes by hand, building tables, searching for any thread of order in the scatter. What he found was remarkable, not a way to predict any individual prime, but a formula that could estimate, with surprising accuracy, roughly how many primes exist below any given number. It was elegant and it worked shockingly well. But Gauss knew exactly what he had and what he didn't have. His formula was an approximation. It told you roughly how many primes to expect, not where they actually were and not why. It was a brilliant best guess dressed up in mathematical language, but mathematics does not run on best guesses. It demands certainty, all the way out to infinity, and Gauss's work, however beautiful, could never provide that. 50 years later, Bernhard Riemann took a completely different angle. Instead of counting primes from the outside, he built a strange mathematical object, now known as the Riemann zeta function, a kind of machine that takes in numbers from a two-dimensional plane of what mathematicians call complex numbers and spits out other numbers in return. Most of the time, the output is just some ordinary value. But at certain specific points, the machine outputs exactly 0. Riemann began locating these 0 points, and when he plotted them, he noticed something extraordinary. Every single one he could compute landed on the same straight vertical line, a line running through the point where the number's real component equals exactly 1/2. Riemann couldn't prove this would hold for every 0, forever. He simply observed it, wrote it down as a hypothesis rather than a proven theorem, and moved on to other work. That single sentence, that all the non-trivial zeros lie on this critical line, became the most famous and proven statement in the history of mathematics. Why does this matter for primes? Because those zeros are not just an abstract curiosity. They are mathematically locked to the distribution of prime numbers. Gauss's approximation wobbles. It overshoots and undershoots the real count of primes in small, unpredictable ways, and nobody could explain the wobble. Riemann's zeros are the explanation. Each 0 contributes a tiny correction, and when you add up the corrections from every 0, Gauss's rough estimate snaps into the exact truth. If every 0 really does sit on that critical line, then the primes are not chaos after all. There's a hidden order running underneath them, encoded in the positions of those zeros. If even one 0 strays off that line, somewhere out in the incomprehensibly distant reaches of the number system, then a huge amount of modern mathematics that has been quietly built on top of Riemann's assumptions starts to wobble with it. This is why, in the year 2000, the Riemann hypothesis was named one of 7 Millennium Prize problems, each carrying a $1 million reward for a correct proof. In the more than 2 decades since, only one of those 7 problems has ever been solved. The Riemann hypothesis is not that one. Mathematicians have since checked more than 10 trillion of these zeros by direct computation, and every single one has landed exactly where Riemann predicted, without a single exception. 10 trillion confirmations and still no proof, because 10 trillion is nothing compared to infinity, and mathematics does not accept probably. This is the wall that stood, essentially unmoved, for 170 years. And this is where the real story, the one worth telling accurately, begins. In 2026, researchers at Anthropic, the AI company behind the Claude models, decided to point an unreleased, more capable research version of their system directly at the Riemann hypothesis. Not as a publicity stunt, and not with any expectation of an outright solution. They gave it the problem and let it work. According to Anthropic's own account of what happened, the model quickly recognized that proving or disproving the full hypothesis outright was not realistic, not for a human mathematician working alone, and not for an AI system either. Instead, it did what a smart, resourceful researcher does when a mountain can't be climbed directly. It looked for a nearby ridge it might actually be able to reach. That ridge was a well-known, narrower question connected to the same zeta function. Mathematicians already knew that a certain percentage of the zeros of the zeta function could be proven, with full rigor, to be simple, meaning non-repeating, and to sit exactly on that critical line. The best-known lower bound before this project stood at around 41.6%, a figure built up slowly over decades by multiple mathematicians refining each other's work. The Claude research model's job was to see if that number could be pushed higher. And it was pushed higher. Significantly higher. The system's work raised the proven lower bound from roughly 41.6% to about 67.2%, meaning it helped establish, with full mathematical rigor, that at least 2/3 of all the infinite zeros of the Riemann zeta function are simple and lie precisely on the critical line. This wasn't the result of one clever prompt or one lucky guess. Anthropic's account describes a sprawling, expensive process. The system explored a huge number of independent lines of attack, most of which failed outright, alongside a handful of promising threads and, ultimately, 2 key breakthroughs that got combined with a separate verification process to check the logic held up. The system reportedly consumed tens of millions of tokens of reasoning to get there. This was not a single flash of insight. It was something closer to a research team's worth of trial, error, and iteration, compressed into one long, exhaustive process. Crucially, this result was not just an AI company's own claim about itself. Independent mathematicians reviewed the resulting paper and confirmed that the mathematics held up. Outlets covering the story, including Scientific American, were careful to draw the same line Anthropic itself drew. This is not a solution to the Riemann hypothesis. Nobody has solved it. The core, million-dollar mystery remains exactly as open today as it was last year, and as it was in 1859. What actually happened is narrower, and in some ways more interesting. A machine took an existing, well-defined open problem in number theory, one connected to but distinct from the full hypothesis, and moved the boundary of what mathematicians can rigorously claim to know. It's worth pausing here, because this is also the moment to clear something up. If you've spent any time in this corner of the internet recently, you may have come across a different, flashier version of this story. One claiming that Google DeepMind's AI uncovered a hidden statistical fingerprint buried inside the gaps between prime numbers, a pattern so shocking that researchers in the room refused to believe what they were seeing. It's a great story. It is also, as far as any credible source can confirm, not a real documented event. There is no peer-reviewed paper behind it, no verified announcement from DeepMind, and no mathematician on record confirming it. It appears to have originated in speculative online videos and blog posts, and it has been circulating since without ever being substantiated. The Riemann hypothesis has, unfortunately, become something of a magnet for viral claims like this. including a joke made by an AI engineer in 2024 claiming a different model had solved it, which was retracted within hours but still resurfaces as if it were true, and separate viral posts about a supposed 500-page quantum AI proof that has never been published anywhere. None of that is real. The anthropic result is. So, why does the real story matter, even without a full proof? Because it changes what doing mathematics might look like going forward. A human mathematician working on a problem like this carries the accumulated weight of the entire field on their shoulders. Every failed approach, every theoretical framework, every unspoken assumption about which directions are worth exploring and which are a waste of a career. That inheritance is usually a gift. It focuses effort, but it also quietly narrows the field of view, because every framework that tells you where to look is also telling you, just as forcefully, where not to bother looking. An AI system exploring the same territory doesn't carry that inheritance. It has no reputation to protect and no sunk cost in a particular theoretical camp. That doesn't make it smarter than the mathematicians who spent decades getting the bound to 41.6% in the first place. Their work was the essential foundation this result was built on. But it does mean the system could afford to burn through an enormous number of failed attempts without ever feeling embarrassed about it, and eventually stumble onto a combination of ideas a time-constrained human researcher might never have had the patience to fully explore. The honest takeaway is this: the Riemann hypothesis is still standing. It has survived 170 years of the sharpest minds our species has produced, and it survived this too. But the wall moved. A number that hadn't shifted in a meaningful way for years. The proportion of zeros mathematicians can prove, with total certainty, sit exactly where Riemann said they would, jumped from under half to more than 2/3, and it happened because a research system was allowed to fail millions of times in private before it succeeded once, in public, in a way that other mathematicians could check line by line and confirm was real. So, here's what I actually want to leave you with. Not a fantasy about a machine seeing some hidden face in the primes that we all somehow missed for 2,000 years. That story sounds better, but it isn't true, at least not yet. What's true is quieter, and in its own way more remarkable. A genuinely hard, genuinely open problem in mathematics got measurably harder to call unsolved because a system with no ego and no deadline was willing to grind through more failure than any one person could stomach in a lifetime. The Riemann hypothesis is still out there and proven, waiting. But for the first time in a long time, the gap between what we can prove and what Riemann simply believed just got a little bit smaller. And if that pace keeps up, the next headline about primes might not need any exaggeration at all.